even multiple polylogarithms, mostly for the one variable case. But even though both topics are connected by a case theory, there was no direct link between them so far. So my goal for at least the first two talks is to give a very direct connection between the Steinberg module and a certain space of multiple polylogarithms. And then in the third talk, I will give an even more interesting link to the Euclid program. So what I want to do, so the talk will start as, in some sense, a continuation of what Clément was doing. So I want to talk about multiple polylogarithms, which we have seen in the first lecture, but we haven't seen a lot of them. And so I'll just briefly recall the kind of naive elementary definition. It's just a certain complex analytic function, which is defined by power series. And almost immediately, I will not use this definition for quite a while, but it's good to know. So in the case of classical polylogarism, we just had a single sum, and in the case of multiple polylogarisms, it's a multiple sum. And the summation domain is a certain cone in the integer lattice. So it's strictly, we sum over all strictly increasing sequences of numbers m1 up to md, and I guess here it should be sorry. So these are the same letters. Okay, so if you remember the last point of yesterday, so the classical polylogarithms, they have a motivic version which lives, so classical polylogarithms, the end, there is a certain, did they use M or H for this letter?
H or
H.
C module.
Yes. Okay, so there's a certain motivic version, NH, which lives in this big algebra. Well, it lives in the nth graded component of a certain big Hopf algebra. And so there is a similar analog for multiple polylogarithms. So there is a kind of a motivic version of multiple polylogarism which lives, well, again, it lives in Hn of f, of whatever field you're looking at, where n is the sum of the indices in this function, which will be the weight. And the other obvious kind of, not an invariant necessarily, but a point of interest is a number of variables in this function, and that is usually called the depth. So depth 1 multiple polylogarithms are precisely the classical polylogarithms we have seen so far. Okay. And there is well, there are several conjectures by Goncharov about these objects. So one of the conjectures actually, if you take the Hopf subalgebra generated by all of these objects, it will actually generate all of the mixed Tate motif Hopf algebra. So my point of view will be actually, I will ignore that part of the conjectures. I will just assume that H is the subalgebra spanned by multiple polylogarithms. And I want to explain a little bit of how the structure. So there are several things you have to then understand: how to multiply these objects and how to take coproducts. And this turns out to be given by simple combinatorial formulas. And then, in principle, you can kind of bypass the fact that we don't know that they span everything, but just formulate conjectures purely in terms of something associated to this combinatorially defined subalgebra. Okay. So first of all, it's not clear from this definition at all that there should be any motivic interpretation, because this is just like some multiple sum. And at least the examples that Clément was given were all given by some relative homology and some algebraic varieties. So there's two actually two sets of functions that I'll be interested in. So one is the multiple polylogarithms, but the other is iterated integrals. And these will be again some objects in this, some elements of this big Hopf algebra, but they're parameterized differently. It's going to be an element in Hn of f, and Ai will be some elements of the field, and I'll probably only assume that they're not the same, but it's not actually necessary. And so what is the definition of this element on the analytic function level? It's just, I will first define it in a special case, and I'll tell what is the difference between this and the general case. So it's just the integral over the simplex, the ordered simplex in n dimensions of a certain differential form, which hopefully the sign actually agrees with what I had in mind. Okay. So, and here, if I want to take the general function with these additional parameters, say 0 and an plus 1, so these encode the endpoint of a more general passive integration. So here I just took 0 and 1, which kind of is represented here. And in general, so we take a class from 0 to 1 with C, which starts at A0, ends at an plus 1. And the naive definition will depend also on the choice of the homotopy class of this class in the complement of all of these points AI. But in this Motivic version, it actually will not depend. So it's just this definition where you take Ti and replace it by gamma Ti. Just literally substitute each gamma Ti, and that would be the iterated integral in general. And so this thing is more clearly Motivic because you have some kind of cycle over which you're integrating. And you can define a variety which is just an with some things removed.
So how is this an element of this Hopf algebra? I mean,
yeah, so this is...
Yeah,
because so...
Or maybe you can remind me again what the Hopf algebra is, because I think it only came up shortly in
Yeah, actually I don't want to do that because that would take me a little bit of time. So you can write down basically a variety and some relative cohomology in which this object will live. And it will be a period of some relative cohomology for an with some hyperplanes removed and modulo some cycle, modulo some subvariety. So I will never use any of the Motivic kind of setup at all, except to say that there is some object in which everything lives, and in a bit I will actually give formulas for all of the Hopf algebra structure on these objects, and after that you can actually ignore the Motivic setup completely. So. In fact, because Motivic setup is somewhat conjectural, there is something concrete you can define without ever worrying about whether like Delix and Solé conjectures hold or things like that. And so you can do computations, you can prove results about these objects regardless of the Motivic setup. So what is the relation between these two functions? It's given by a change of variables, which is a little bit long, so because I have to write a lot of things, most of them are 0. So the multiple polylogarithm in weight n, so the weight will not actually enter here. is going to be exactly the same as the iterated integral. Except you have to write a very long list of points AI. One. And so, in fact, for xi less than or equal to, well, I guess, strictly less than 1, this is an actual identity between analytic functions. So if you write down this integral and that sum, they're actually equal, and that's an exercise.
Sign?
Yeah, that's the, thank you. So there's a sign here, which always kind of makes things, I mean, I'm always making mistakes, doesn't it? So, and so I'm always going to write all the functions without this H script. But here, just to emphasize that this identity is also true in the motivic setting.
But it's also just true as a literal function.
Yeah, it's true as a literal identity. Yeah, the only problem is you can't take this proof. I mean, you can take this as a definition of what is motivically 1 and 1, and so on. Because I haven't defined, here I at least said something about why this is an element in HNFF. There, you basically can just say this is a definition.
Well, but they're both functions, right?
No, as functions, it's all fine.
Okay, good.
But I haven't given you a separate way of defining what this thing is a motive. So I just said this, because this is an integral of something algebraic on algebraic variety. There is some kind of motivic interpretation. And this is a multiple sum, so there's no like theory of like discrete motives. Okay. So, that's fine. So basically, Hn of f, for me it will be generated. So it's a Q space on all dn1 and d of x1 d, where n1 plus and d, they're always going to be summing up to n. D is going to be anything I want, and I are going to be always positive. And x1 up to xd are going to be elements in the field. And you have to quotient it out, basically. So if you think of this as formal symbols by all functional equations, functional equations. So this is basically a way to define it without referring to the conjectures of Goncharov. And the only problem is if you try to define it in this way, you have to say what the functional equations are, and in fact, this is a difficult problem which we don't know how to solve in general. So I want to just give you an idea about some functional equations that are always true, and about the structure of the coproduct, and then I will try to make a connection with the Steinberg model. So functional equations, we already have seen a few. I mean, the simplest one is, well, log x, which is v1 of 1 minus x. So it satisfies the obvious functional equation. So Clément gave a functional equation for the dilogarithm, so there's a 5-term. Which I won't write down, so this is a function equation for E2. And in fact, if you try to do this story for classical polylogarithms, you quickly run into some problems where basically after some point we almost know no functional equations for classical polylogarithms. But there's a different type of relations which figured in Clément's talk but was not explicitly mentioned. So this is the so-called depth reduction identities. And this will be a subject by Stephen Charlton. So I'll just give one example of what it is. So it's identities which relate functions of different depths. So far, this is like depth 1, so it's just an identity in one function. And we haven't seen identities which mix different things. And so I just want to give one example, and then maybe Herbert will tell me where the signs are wrong. So here's an example of an identity which relates a function in two variables to one to the classical diloggers. So actually, the weight is a very nice part of the Hopf algebraic story because it's a grading, but the depth is a little bit more mysterious, and in fact, part of the conjectures of Goncharov is explaining what the depth filtration looks like. Yes?
No, it's okay. I answered my own question.
Okay, so
sorry, I want to clarify things for me, right? So that's why I'm asking so many stupid questions. Sorry about it. But is the upper line a definition? Is this motivic? Is this? Should I just say that HNF is the is by definition just a subring of functions given like this?
Yeah. Okay. So if you kind of believe in that Hn of f exists for all fields, then you just take the sub Hopf algebra generated by these objects. Or in fact, you just take the vector space generated by them over Q, and that would be conjecturally the same thing. And I will basically describe the structure on this part of the mixed state Hopf algebra.
Is it known that for some fields that the Hopf algebra is...
I think for number fields it is known
that it's generated by the... So in which, what is this equation? Is this a conjecture?
So in any case, this is not an equation.
I don't know if everybody saw, but Clément shook his head. People back here could not see that necessarily.
I mean, I don't think it's known for any field that the motivic Hopf algebra, let's say for number fields, is spanned by...
Okay, it's known in some cases, but not in general.
For very small n, I guess.
Okay, then this is just basically an idea, so one can treat this whole story in a way which looks like elementary. So you just try to study these functions and the functional relations that they satisfy, and then you can define this Hn of f kind of in purely explicit terms. And so the problem is, from this point of view, we're lacking this part of the definition. So
and we don't even know what the functional equations are yet, right? Is that right?
In fact, we will not find out what all of the functional equations are because we don't know them. I mean, we know some of them.
But could so these things sit. Well, we could define an algebra that sits inside of the Hopf algebra generated by the Lie stuff, yes. and that would be a Hopf.
So in cases where
there are some relations.
In cases where the motivic story works, we can define a subalgebra generated by these polylogarithms.
Yes.
And we still wouldn't know what functional equations are, but we would always know when something is equal to 0. So I mean,
but then you can actually define what it means to be.
So okay.
There's relations in there.
So there is a way to define what the functional equations are, kind of, without relying on any conjectures. And that is basically, you have to use the Hopf algebra structure, and then in weight 1 you know everything, because there you actually know it's just f cross rationalized. And then you basically define what functional equation is by saying it's something whose coproduct is 0 specialized in different ways. And so that you can define what the functional equations should be, but then it doesn't tell you what is a generating set. So it doesn't tell you what. It's kind of a moot point, so it's not what I want to talk about at all. And in fact, until recently, we didn't have any even conjectures about what should be the generating set for the functional equations. So nowadays, there's at least a few classes of identities which I think should be enough, but again, everything is mostly conjectural. And the point of this talk is actually to avoid all the conjectural stuff. So I just want to do some explicit calculations to convince you that you can find the Steinberg module inside this story.
It'd just be helpful for me if you say in which world these calculations live in the end. That just personal thing.
Yeah, okay, so I'll define more of the structure in a moment, and then maybe it will be clearer. Okay, so another thing is, so far these were somehow special, and again, depth reduction is a complicated story that Stephen will talk about more on Friday. So there's part of Goncharov's conjecture which actually described how depth reduction should work in general. So what kind of combinations of multiple polylogarithm can be expressed as multiple polylogarithms of strictly lower depths. And this is not the subject of this talk. So there's in fact, three families of identities which are quite general. And these define part of this Hopf algebraic structure. So basically, I haven't told you how to multiply these things. And of course, in the motivic setup, it's clear, but here I have to do something. So there's shuffle products, and quasi-shuffle products. So there will be two ways actually of multiplying objects, multiplying these elements. So one based on multiple polylogarithms and one based on iterated integrals. So I'll just write down the formula. Actually, I don't want K0, so the formula will be giving you a multiplication rule for two iterated integrals. And it's given over, so I have to introduce some notation. So I guess sigma n we already had this as a symmetric group. And I will introduce the notation for sigma kl for the space of all shuffles. So it's sigma in the symmetric group for which the preimages of the first k elements are ordered and the preimages of the last L elements are ordered. And so the formula will be given as a sum over all shuffles. Maybe it's not the best notation because it's a sigma and sigma, but so this tells you how to multiply things if they're given as iterated integrals, and the other formula is the same thing, but how to do it in terms of multiple polylogarithms, and it will be very similar, except it will not be exactly the same. So it's exactly the same setup. We want to multiply two of these things. And there will be a part which is just the sum over all shuffles, but there will be more. And that part I will not write down. So now, in the case of iterated integrals, you just shuffle around the arguments inside these two functions, and for the multiple polylogarithms, you shuffle both the arguments and the indices simultaneously. And there will be plus lower depth contributions, which are a little bit more of a pain to write down. So what I'll do, I'll just give you one simple example. So, example, well, for the kind of for the iterated integrals, it's a little bit boring. So it's just going to be a sum of two terms. But for polylogarithms, you have an extra thing. So if you multiply Li1 of x and Li1 of y, which is just a product of two logarithms, you get Li11 of x comma y plus Li11 of y comma x plus, and the third term, which is not here before, is Li2 of x times y. And so in general, the terms that I didn't write here would be some kind of degenerations of this, the general term, where you allow the neighboring indices and variables to collide, and then you replace them by products. So here it's actually 1 and 1 you allow to collide, and then you get Li2, and then x and y you get x times y. And so the the two identities are actually very easy to prove, but if you try to prove this identity by rewriting it in terms of polylogarithms.
What do you mean prove the identity? Isn't this a definition of what the left-hand side means?
What's
the definition of the left-hand side?
The problem is, no, it's, okay, so if you view these as motivic things, then that's actually not exactly the same. I mean, it's not a definition. Okay, so let me kind of go back to motivic setup. So this would be a product of, we just take kind of direct and remove your motive associated here, and this is do something completely different. On the level of kind of, on an elementary level, this also makes sense. This is an identity, but so this is basically the fact that you have the iterated integral, and I think that is still here.
True as a number, like if you plug in.
Yes.
So if you just plugged in complex numbers into the A's, you would get this identity.
In fact, the proof is kind of almost trivial if you just take this definition and multiply it with the definition for you immediately see where the shuffles come in because it's basically you're splitting the product of two simplices. I mean, you're triangulating a prism. That's what's going on. And exactly the same proof actually gives this identity, except you start with this multiple sum definition of polylogarithms. Okay. So I guess it is maybe a little bit confusing because I'm jumping between different points of view. So for now, let's just think of everything that I write is in the Clement setting. So I'll just assume that everything works. But there is a way to do it without assuming conjectures. Okay. So this is basically giving you not just one way, well, it kind of gives you two products, which is good. But what is actually good is, because you have two ways of writing products, it gives you the first kind of non-trivial identity between these elements, where this sum is actually equal to this sum. So in particular, if I rewrite iterated integrals here as multiple polylogarithms, I will get a non-trivial identity relating these, which is what plays an important role in the multiple zeta value story, which I will not talk about. And so these are the easiest, and in fact, if you want to get anything else, these are the easiest functional equations to write down, and anything beyond that is actually hard. Except for one other identity. So it's the distribution relation. And that is, so this is easier to write, I guess. I mean, it exists in both settings, but it's kind of the same identity. So if I take d variable multiple polylogarithm and I sum up over all, so it will depend on a choice, well, I guess it will be a positive integer for a moment. Okay, I'll write write it all out. So you take basically all possible nth roots of the variables and sum everything up. Then the result will be, again, the same we started with, except you kind of pick up an eigenvalue of something. So it's so here d is the depth as before, and n is, as usual, is the weight. Right. So in particular, there's a version of this for iterated integrals, but it turns out to be the same identity. And there's another identity which I'm not talking about, which is, here I said n is a positive integer. In fact, if n is a negative integer, this is still true modulo some corrections, and this is more difficult. So n less than 0 is also true, but more complicated. So, I mean, it's not literally true. There's some additional lower depth terms that you have to add. Okay. So, so far I haven't really explained a lot of the Hopf algebraic structure. I mean, I explained how one can multiply these things regardless of what your setup is. And there's even two combinatorial formulas you have. So the other thing is, I want to explain is the coproduct. And so Clément was talking mostly about cobrackets. I will give the Hopf algebraic part. And the coproduct is easier to write down a formula. It's easier to write down a formula for coproduct with its integrals. So again, it will look like a scary formula. In fact, I will not explicitly use it much, except in a few examples. But I'll at least explain what it looks like combinatorially. So I want to, I need to define some kind of tensors starting from this iterated integral. And the idea is you take, so I'll first write down the formula and then I'll explain how to work with it. So there will be one. The summation goes over all subsequences, increasing subsequences of indices between 0 and n plus 1, starting at 0 and then at n plus 1. And there is a left-hand tensor, which is just one iterated integral, and the right hand, which is the product. And in a second, I'll give a nice way to do it. Okay. So I'm pretty sure this is not kind of intelligible in any way. And there's lots of indices. Oops. And the logic is maybe not clear. So what's going on is there is a pictorial way of doing it, which is maybe a lot easier. At least for me it is. So you kind of take a semi-arc and you label certain points in that semi-arc by your variables, so x0, x1. So this, the ones at the end points are x0 and xn plus 1, so they start and the end of the path, and then you have everything else somewhere in between. And so the idea is you take the sum goes over all subsequences of indices, which you can think of as subpolygons inside this arc. So you draw some kind of subpolygon, and each kind of side of this polygon determines your kind of the upper part, which would be again an iterated integral. So here it would be I of x0, x1, x2, x3. So this one here. There will be something here which I don't know. I mean, maybe there's many of them. And here you'll have I of x n minus 1, xn, xn plus 1. And so these, all of them together, when you multiply them, they would give you the right-hand tensor in this formula. And the left-hand tensor here, it's exactly this. So the interior, inner polygon. I don't know, hopefully this is clear. If not,
Sorry, what are the indices in the polygon?
yeah, so you haven't actually, I guess let me give this, for this particular example, it would be I of x0, x3. So you take the vertices of this sub-polygon that you picked, xn minus 1, xn plus 1. So it will always start at x0, it will always end at xn plus 1, and there will be some set of interior vertices which is labeled by these indices. Okay, so so in fact, this is almost everything we need to define.
So this is a definition now. There is no.
No, I mean
Is this a functional equation in some sense?
No, this is literally so. Okay, so there is this Mativik-Hoff algebra, and if you do the calculation there, this is literally what you get.
Okay, that's good too.
So delta in
In
But the point is, okay, so all of the calculations in this sub-Hoff algebra you can just perform directly. You never kind of have to do anything more complicated than this formula. And the shuffle products, I guess. But, if you mod out the products, then you actually don't have to worry about shuffle products either. So you just have to think about something like this. And now there is a way to, like I said before, I will probably, that was not a good idea, but there is a way to avoid all of the conjectural parts and just work with this combinatorially defined Hoff algebra. And then the only question is how to define the identities. And I will not do that, but there is a way to do it without reference to any kind of complicated conjecture. So you can just define a Hoff algebra for any field, whose generators are iterated integrals, whose product formula is given by shuffle product formula, whose coproduct is this. It's going to be graded, connected, commutative. So there will be automatically the the antipode, yes. So, and in fact, the antipode I don't want to think about at all. And then the question is, what do we define as identities? So it's not kind of the free Hoff algebra given by this data. The identities are a little bit trickier to define, but basically the idea is anything which lies in the kernel of coproduct should correspond to some kind of identity, but maybe you have to be careful about. It's not literally everything which is in the kernel of a coproduct is zero, but it basically tells you what should be the identities. So there's some problem because the coproduct of Lie 3 of 1 would be 0, but it shouldn't be 0 in the function. Okay. So far maybe this has been a little bit general and somewhat vague. So for the rest of the talk, I want to basically find the Steinberg module inside this story, and then tomorrow I will explain more about the connection.
So, you said that the coproduct of Lie 3 of 1 would be 0.
Sorry?
You just said the coproduct of Lie3 of 1 would be 0.
The coproduct of Lie3 of 1, I mean, the way I look at it, wouldn't it be 0?
Zeta 3 be...
The slope of 1 is 0.
Shouldn't it be 1 zeta 3 plus zeta 3 tensor 1?
1 zeta 3. No, but, no, okay, sorry. Yeah. Ignore it. Ignore the comment. I was thinking about symbols, sorry. Yeah. Okay, so, no, just ignore the comment. So this was not correct. So let me go to the part about Steinberg module. And so I basically want to give one example of this calculation, which is going to help with the connection. So we already saw, I think in Clément's talk, we had this formula, 1 of x tensor log x. So there's a similar formula like that for the classical polylogarithms. So for the connection to Steinberg, basically one can start with a single formula and stare at it for a little bit and see something. And the formula is basically the coproduct for the Lie1,1 function of x and y. And I will write it out. So it's only 3 terms. So you have to, I guess it's an exercise with the formula that I gave to see that the results is going to be exactly what I write. So it's going to be Lie1 of xi tensor Lie1 of y. So only Lie1s will appear because there's nothing else in weight 1. So this is the formula for the reduced coproduct in the weight 2 for the Lie1,1 function. And so basically I just want to convince you that this is a direct relation to the Steinberg module. And so what is it exactly? So these are all elements in f cross tensor f cross. I mean, I guess rationalized. And if you think, I mean, if you work a little bit with the with this Hopf algebra, you'll see that not arbitrary elements in this tensor product will appear. And here, in particular, there's one kind of integrability condition that they have to satisfy. And so here, this integrability condition becomes completely combinatorial. So what I want to say is, let's think of these 3 elements additively. So instead of, well, I will not write Lie1 at all. I will ignore it. And instead of writing product of x and y, so replace x by v1, y by v2, and tensor product will just be a separator. So then I can just write these 3 terms in the following way. So v1 plus v2 would be xy. I ignore the Lie1. Y would be v2. Then the second term will be v1 plus v2 minus v1. And the third term will be v2 v1. And I mean, this notation is kind of suggestive because these would be elements in the Steinberg module. And if you think about Steinberg module, this is actually 0 in Steinberg of, well, I guess, Steinberg of V, where V is whatever this 2-dimensional space. And in fact, the same calculation kind of works if you started with Lie1,1 of x to the a, y to the b, x to the c, y to the d, with a, b, c, d integers with determinant plus minus 1, you would kind of see the same abstraction. I mean, you will see only elements in the tensor, in the coproduct, whose kind of this naive map to Steinberg module will be be 0. And this is basically the starting point for what I want to do next. Here.
A quick comment. I think you want to sum over the k on the right-hand side of your co-product.
Sum over k. Well, it's implicit because I didn't say what k is. I will not do that. But it's over all subsequences, and the length is not fixed. So. Okay. Right. So I want to kind of use this observation and define a certain set of polylogarithms which will be much more directly related to the Steinberg model. And then maybe tomorrow I'll explain it a little bit in more detail.
Sorry, can I ask, in the line about the Steinberg module, what does square brackets v, comma, w mean? I mean, what does this square bracket notation mean with two vectors in it?
Well, this is just an element in this is an apartment class in the Steinberg module.
Is the apartment generated by that?
I guess it's maybe not agreeing with the notation, so maybe. So for me, when I write this, it should be literally the same as the notation from Jenny's talk here.
I switched back and forth.
Oh. Yeah, in any case, whenever I kind of, I will use both at some point, so this would be the same. So I want to define a certain space of...
Minus v1 doesn't mean anything, really?
Well, here it does, for the Steinberg it doesn't mean. There's actually, it means something in the polylogarithm story, and that's what makes it a little bit more complicated.
But this is just a Steinberg relation in like, so tensor product of multiplicative field, yeah? Like in Miller case theory.
You want to do something much more general. So you don't just take the group generated, I mean the multiplicative group of the fields. You take something much more.
So Li1 of x inverse is not the same as Li1 of x.
Okay, yes, so this is a good point, and this is basically what makes the story quite a bit more involved than it should be. So Li1, sorry, is equal up to logs. And so if that were literally the case, the story would be much more simple, but I mean, I think it would, yeah, I mean, it wouldn't work. So it has to be like, okay. So what I want to do is I want to basically, so I will work on a torus of dimension d. And I will kind of try to define you a space of polylogarithms of this type on that torus. So here we kind of, you can think of x and y as two variables on a two-dimensional torus. And we had monomials as arguments for polylogarithms. So I want to take a more general version, except it requires more. So basically the starting point would be, I take the d-dimensional torus. And so if you think about the material setup, everything will be about the field F, which is kind of far too big for what I want to talk about next, but it will definitely contain everything I will talk about next. So you take the algebraic closure of the field of functions on TD. It's going to be much smaller than that, but I just don't want to worry about it now. And I want to define so I will have multiple polylogarithms evaluated certain monomials, and I'll parameterize them by matrices, by integer matrices. So the input will be a d by d with determinant of a not equal to 0, and kind of shorthand a lot of vector notations. So whenever I write things like x to the n, I actually mean the vector x1 to the n, e to the n. And when I write x to the power matrix, it should be read as matrix multiplication, but in exponents. So it's d a d1, x1. X1, A1D. So it's just going to make my life easier. And I want to define a space of functions Lille. So I'll first write out the indices completely. And it's going to be essentially a monomial transformation given by A acting on the variables, except if determinant of A is not 1, I have to do something more complicated.
So you don't just want A to be determined plus or minus 1?
Yeah. In fact, I want all of the non-determinant ones. Yes. I mean, if I didn't do that, I could already define you something. Basically, take the GL dz acting on the torus and take this as all of the functions that you can obtain by this action. And you can obtain, you get a GLT-Z representation in that way. The problem is, I mean, we can't say much about that representation that's interesting. So I need to go kind of from Z story to Q story. And for that, the formulas will get more complicated. So I'll say N is absolute value of determinant of A, and D minus n minus d minus 1. So there will be some kind of normalization factor which you shouldn't think about at all. But the point is you take exactly the type of thing we had for the distribution relation, but you combine it with the monomial, with the action of GLD on monomials. Okay. And this is, this is going to be everything that I will worry about today. Well, now.
So then K equals D, right?
No, actually not. So if K is less than D, it's also okay. So K is less than or equal to D.
But how do you evaluate Li N1 and K?
It's kind of, you think of this as a function on the first like K variables out of the.
Oh, okay, you just take the first K variable. All right.
Yeah, I mean, it's not a very canonical way of doing it, but I will in a second just mod out everything which is lower depth, so that wouldn't matter. Okay, so this is basically all of the functions I care about are going to be of this type. And I'm over time, but sorry. So I want to define some, I'll do it quick. I want to get to the Steinberg module. So Ln of Td is going to be the Q span of all of these functions. Okay, so all of these indices and matrices. Modulo, and this is all inside Hn of that huge field. Modulo the subspace given by all lower depth functions, so the same thing. Q span of the same thing, but with K strictly less than D. Plus anything that I logarithm of one of the coordinates times anything from the same type. And here again, over the same conditions. So basically I take all of these functions and I ignore everything of lower depth, so which involves not D variables. And and everything which can be written as a product of logarithm of one of the coordinates times something of lower weight. And this part actually exactly corresponds to this issue. So the fact that Li1 of x and Li1 of x inverse are not the same. And now the main theorem, and I will stop here. So this is from a joint paper with Charlton, Radchenko, and myself. So this is, in fact, in a natural way, a GLDQ module. And the fact that not just GLDZX, GLDQ is directly related to the distribution relation. And this GLDQ module is, well, so there is a map going from ln of 2D to Steinberg q to the d, tensor Steinberg q to the d, tensor asymmetric power of q to the d of degree n minus d. Okay. So the claim is, well, there is an isomorphism between these two modules, which is already non-trivial, but in fact, I can tell you what happens to the generators. Here. And I will repeat this story actually tomorrow. So on the generator, without all of the analysis acting, it's going to be just an explicit formula like this. To answer some polynomial. And I will start the next lecture with this theorem and explain it in more detail.